Hi friends, today we are discussing about the non-linear pharmacokinetics coming under 6th semester B.Pharm Biopharmaceutics. Whatever the topic, in biopharmaceutics, equation as well as the diagrams are very important. First we have to draw the models or diagram, then we have to derive the equation. If equation is there, we have to substantiate which represent, for example, dc by dt represent, like that we have to represent. So let's have a journey through the nonlinear pharmacokinetics. Nonlinear pharmacokinetics. Here in this kinetics, the process depend on carrier or enzyme having a definite capacity, and the change in concentration is not proportional. That's why we are telling as non-linear. The pharmacokinetics of the drug, we can see a transformation of the first order kinetics into a mixture of first order and zero order. So we can tell that the pharmacokinetics of the drug as dose dependent, or other name of the nonlinear pharmacokinetics are mixed order, nonlinear and capacity limited kinetics. So we can see the changes in different pharmacokinetic parameters. These changes are the reason or causes of the nonlinearity, like drug absorption, distribution, metabolism, and drug excretion. Today we are focusing on the Michaelis-Menten equation. When you heard about this equation itself, you have to know it will come under non-linear pharmacokinetics. So non-linear pharmacokinetics, we already expressed this kinetics is capacity limited of a saturable process, and this can be best described by our Michaelis-Menten equation. So now down the equation, that is minus dc by dt is equal to Vmax into C divided by Km plus C, where max and m are representing as a subscript. So we have to express what is dc by dt. Here it is minus, so we can see a rate of decline of the drug concentration proportional to time, where Vmax is the theoretical maximum rate process and Km is our Michaelis constant. So depending upon the value of Km and C, we can tell three conditions. So this is the way of expressing the Michaelis-Menten equation. From this we can see the nonlinear pharmacokinetics. For that we have to plot dc by dt on y-axis and concentration on x-axis. So this is the type of curve we can see. So initially the rate increases linearly. So we can tell up to this it is first order. With concentration it becomes what? Mixed order kinetics, and then it reaches the maximum. The maximum we are representing as Vmax. So this is first order, mixed order, and going at high doses to zero order. Means it is going to a constant rate. So this is a Vmax. So half is Vmax by 2, and we can express this condition in terms of three conditions. First one, when Km is equal to C. So when the Km become equal to concentration, we can tell the equation changes to minus dc by dt. Here Vmax into C. So Vmax and C is equal. So we can tell here become Vmax by 2. Next case, when Km is very greater than C. So in that condition, we are telling this Km plus C is equal to a Km. So instead of that, we are introducing a new constant, that is Km. So the equation becomes minus dc by dt is equal to Vmax into C divided by Km. And the third condition is that when Km is very less than compared to concentration. So what happened? Here instead of Km plus C, here we put it as K. M. Here we are telling Km plus C is equal to C. So this equation is identical to follow zero order, and in this condition the equation becomes minus dc by dt is equal to Vmax. That is, it describes a zero order process, and zero order means it is independent of the drug concentration. For example, in case of metabolism of ethanol. So our initial equation is minus dc by dt is equal to Vmax into C divided by Km plus C. So on that equation we are going to integrate and converting to the log base 10. So the equation becomes log C is equal to log C0 plus C0 minus C divided by 2.303 Km minus Vmax into divided by 2.303 Km. So when we plot the C versus our time, we get a curve with a constant with a terminal linear portion having a slope of Vmax divided by 2.3 in this part. And when we back extrapolated to the time 0, we are getting an y-intercept, that is we are putting as log C0 back. So the equation becomes log C is equal to log C0 back minus Vmax divided by 2.303 into Km. As we said earlier, when we back extrapolated the thing, when we plot log C versus T, we are getting a plot like this, and we back extrapolate log C0 back we are getting, and the terminal linear portion of the curve will produce the slope, that is minus Vmax by 2.303 into Km. So what happened? At low plasma concentration, the log C and log C back values become equal. So we can simplify the equation as C0 by C divided by 2.303 Km is equal to log C0 back by C0. So we can easily obtain our Km from this equation, while we can obtain our Vmax value by putting value of Km. Next we are going to think about the IV infusion in case of a steady state concentration. For example, when a drug is administered as a constant rate IV infusion or in a multiple dosage regimen, how is the dosing rate? So dosing rate dr is equal to Vmax into CSS. CSS means steady state concentration divided by Km plus CSS, where we know dr dosing rate is equal to CSS into CLT. So in case of IV infusion, what happens? dr become equal to R0, and dr is equal to, we already studied, Fx0 by tau. So when we plot the steady state concentration versus dosing rate, we will get a plot like this. And this plot we are telling is a hockey stick shaped curve. So this is a curve for a drug which follow non-linear kinetics when we plot a steady state concentration versus dosing rate. Next, we are going to define the characteristic of the curve by computing the Km and Vmax in three ways. First way is that with the help of Lineweaver, Burke plot, or it is otherwise known as Klotz plot. So here what we are going to do is taking the reciprocal of our dr equation. That is, in our previous equation we studied dr is equal to Vmax into CSS by Km plus CSS. So we are going to take reciprocal, and we get 1 by dr is equal to Km divided by Vmax into CSS plus 1 by Vmax. So when we plot the 1 by dr versus 1 by steady state concentration, which will yield a straight line with a slope of Km by Vmax, and we will get the y-intercept as 1 by Vmax. Second method is direct linear plot. Here what happens is that we are plotting with the help of a two pair, that is a pair of CSS, that is CSS1 and CSS2. We are plotting with two different dosing rate DR1 and DR2, and when we join to form a line, and second line is obtained similarly by joining one CSS2 versus DR2. So the point where these two lines intersect, when we extrapolated to the dr axis, which helped to obtain what? Vmax. Third method is graphical method. Graphical method we are also using to determine the Km and Vmax. Here what we do is we are rearranging the equation and we are getting dr is equal to Vmax minus Km into dr by steady state concentration. So when we plot this dr versus dr by CSS, we will get the slope as minus Km and y-intercept as Vmax. So these are the three ways by which we can find out the Km and Vmax. So there are several limitations of Km and Vmax estimated by assuming one compartment system. So we are moving to the complex equation. However, the Km and Vmax we obtain by circumstances have little practical application in dosage complication. So these are main points coming under the nonlinear pharmacokinetics. Especially you have to study the Michaelis-Menten constant, Michaelis-Menten equation. What are the different methods for estimate Km and Vmax? I hope this video is helpful for you. If you find useful, please share it to your friends. Thank you for watching.